8 told us the significance of the direction of the cross product, assuming, of course, that the cross product isn't 0 and that it has a direction. Theorem 9 is going to tell us something about the significance of the magnitude of the cross product. And that's going to be if A and B are not 0. So neither one of them is the 0 vector, which means there's an angle between them. So theta is the angle between A and B. Okay. Then the magnitude of A crossed with B is equal to the magnitude of A times the magnitude of B times sine of theta. Notice if this were cosine, this product of three things would be what the dot product is. The magnitude of the cross product is the product of the two magnitudes and then sine of the angle between the two vectors. Now what I've done up here is I've drawn in the 5 possibilities we have for what the angle between our vectors could be. They could be parallel and pointing in the same direction, which would make theta be 0. Theta could be acute, it could be obtuse, it could be right, it could be obtuse, or my vectors could be parallel pointing in the opposite directions, which would make theta equal to pi. What I'm going to do is use these pictures to illustrate what this product actually represents. Because in all cases, that's going to represent the area of the parallelogram with A and B as adjacent sides. Now if I start here, where the A and B are parallel, pointing in the same direction so that the angle between them is 0, these guys form what we call a degenerate parallelogram. There's no height to it because A and B point in exactly the same direction, so the area of a degenerate parallelogram like this with 0 height would be 0. But if I take a look, if theta is equal to 0, sine of theta is equal to 0. So this product, which is the magnitude of that cross product, is going to be 0, which does correspond with the area of that degenerate parallelogram. Now, if I look at the case here, where theta was acute, if I draw in that parallelogram right there, I can say, well, the area of that parallelogram would be the base times the height. Now I can take as the base this side here, so that would be the magnitude of A, but then to calculate the height, that's not going to be the magnitude of B, because I know the height I'm going to get by dropping a perpendicular here. But I can then just use right triangle trigonometry, and I can see that sine of theta, if I call this H, sine of theta here is equal to H over the magnitude of B. So the height would simply be the magnitude of B times sine of theta. So again, this magnitude of the cross product represents the area of that parallelogram. Now in the case that theta is a right angle, the base would be the magnitude of A. The height would just be the magnitude of B, because now B is already perpendicular to A, but sine of theta, sine of pi over 2, would be 1. So that formula still works. Now if I'm looking in this case, that theta is obtuse. Okay. Now, once again, the height I'm going to get by dropping a perpendicular here. So I can say the base is the is the magnitude of A. Now here, this would be pi minus theta. The supplement of theta would be the angle that shows up in this right triangle, where I'd say the sine of pi minus theta is equal to H over the magnitude of B. But if I look at supplementary angles, they have the same sign. So this is the same as sine of theta. So once again, the height is just the magnitude of b times sine of theta. And then, in this last case, here again, A and B are parallel. They're just pointing in opposite directions, but that means that they form a degenerate parallelogram. There's zero height when I try to draw in a parallelogram here, so the area of the degenerate parallelogram would be 0, and with the angle between them being pi, well, sine of pi is 0. Okay. So, for non-zero vectors, the significance of the magnitude of the cross product is that it is the area of the parallelogram with those two vectors that I'm crossing as adjacent sides. And of course, if one of my vectors were 0, then the cross product is going to be 0. Well, I'm not getting any sort of a parallelogram in that case, and the magnitude of the 0 vector is 0. All right, excellent. Now, I've discussed what this means. I didn't prove this, and I didn't prove Theorem 8, which showed that the cross product was going to be mutually orthogonal to the two vectors that I was crossing. Both of these are proved in your textbook, and they're proved simply by writing the vectors that we're crossing at the component level. So to prove that A cross B is orthogonal to A, you work out what A cross B is in terms of the components. You'd use arbitrary components. So you'd have to write A is A1, A2, A3, B is B1, B2, B3. You'd have to work out the cross product in terms of those components, and then you'd have to work out the dot product. It's basically a lot of tedious calculation. Okay. Good to know that that's how you would prove it, but that's not one of the proofs that I consider particularly enlightening. It's more just plug and chug and you get the right answer, but working through the proof doesn't really explain why it's true. Sometimes when you work through a proof, that helps you to better understand the thing that you were proving. Here, I think proving these theorems, while it's a useful thing to be able to do, and it's definitely important to know that you would prove them by writing things at the component level, working through the proofs is just plugging and chugging through some calculations, and I don't feel enlightened at the end. I don't feel like I understand anymore why it's true. The book also proves this theorem. Again, they do that by writing things at the component level, and then using the fact that cosine of theta, we've got a formula for in terms of the dot product and the magnitudes of our two vectors, and for angles that are between 0 and pi, so since theta is in the interval from 0 to pi, sine of theta can be written as just the square root of 1 minus cosine squared theta. It's always either that or the opposite of that. Because we're in the interval from 0 to pi, we can take the positive square root because we know that sine of theta will not be a negative number in this interval. Okay, so those proofs are in your textbook. I would encourage you to read through them and to recognize that you can prove these things by working with things at the component level. Again, though, I'm not going to spend time in class working through them because I don't feel like they lead to a better understanding of why things are true. I try and sort of pick and choose the proofs that we do to be the ones that help us to understand the concepts a little bit better. All right, now this theorem, Theorem 9, does have a corollary. If you look at these cases, you'll notice that the only times we got degenerate parallelograms, which had 0 area, were when the vectors A and B were parallel to each other. Any other time, if A and B are non-zero vectors and they're not parallel to each other, we're going to get a non-degenerate parallelogram. It's going to have some area, so this magnitude is not going to be 0. And that means that the cross product is not 0. So corollary 10 states this. If A and B are both not the 0 vector, then A crossed with B will equal the 0 vector if, it looks like I misspelled the word if because I spelled it with 2 F's. That actually stands for if and only if. So that tells me it's a two-way implication. A cross B will be the zero vector if and only if A is parallel to B. And I can denote that two vectors are parallel by just putting this parallel symbol in between the names of the two vectors. So that says if the cross product is the zero vector, and I started with two non-zero vectors, that tells me that they're parallel. If two non-zero vectors are parallel, then their cross product will be zero. So I alluded to that fact earlier. Now we can actually see why it's going to be true. Okay, excellent. So let's see, we've been going for a little while. Well, in the next video, we'll actually do an example of using this theorem.